Okay.
Right on time, the last talk of our reunion, Stevan Nadj-Perge, correlation, superconductivity, and Chern Insulator, and twisted bilayer graphene stabilized by tungsten desalinate.
Thank you, Andrey. Thank you, organizer, for giving me this chance to talk about our work. And before I guess I dive in, I'll just gonna acknowledge my group. Most of the talk today will be on the work that has been done recently by Harpreet, Robbie, and Eun-Ah, and if I have time, I'll kind of touch upon the contributions of the other members. And over the years, we benefited from discussions with theorists at Caltech, Jason and Gil, and Young, Peng, Alex, and Cyprian, who recently joined. We got materials from NIMS and University of Washington, and had some kind of had funding from NSF and DOE. So I'm actually going to go a little bit kind of back to the basics and kind of try to basically summarize why do we need a magic angle, and look in this into this context of correlation energy and kinetic energy as a bandwidth. And there's a beautiful figure in the original paper from MIT which kind of summarizes basically this diagram, and it says, that just at the magic angle, your bandwidth is supposed to go to 0, and if you reduce the angle, you basically the correlation energy kind of decreases. But there is this region where the Coulomb interaction actually overcomes the kinetic energy, and this is where you want to be if you want to see all these effects. And this looks like nice in theory, and the reason we can kind of understand why U is changing when you change the angle, because if you change the angle, you kind of see this difference between the distance in AA site, where people are where the distance between the electrons is kind of increasing as you lower the angle. However, if you think about this experimentally, there's a huge discrepancy in this bandwidth in what theory finds and versus experiment. And moreover, we don't really know how to define this bandwidth. We don't know what's relevant. Is it the distance between Van Hoff singularity peaks? Is it the width of Van Hoff singularity peaks? Is it, where the Fermi velocity goes to 0? And some of the, last year's STM experiment, including ours, tried to kind of answer these questions. And I think the best answer that we can give is, experimentally, this bandwidth, first of all, the scale is a little bit wrong. This bandwidth never really goes to 0. It goes to some finite value around the magic angle. And then, in addition to unknowns on the bandwidth, it's another question is how to measure this correlation. So how to measure this energy U. And the best thing we can say is, in transport, you measure either you see insulating states or you don't see insulating states, and either you see a superconductor or you don't see a superconductor. So this is kind of something that you want to learn about this U over W. But the fact is that we don't know how to measure it, but we know how to change it. So we know how to change U, and we saw a beautiful example in the last talk. You either can change this by screening or by change of angle, and then you can change the bandwidth by changing the angle. So if you move away from the magic angle, your bandwidth will increase, and basically your ratio between the correlation energy and the bandwidth will decrease. So in the last, less than a year, there were like 4 different works, including ours, where, various groups try to control this ratio and see what happens, basically. So here, there is example where you make some statistics, you change the angle, you change the thickness of HBN, And you kind of hope you will change your correlation energy, and in the last one you can change the basically effective thickness or the electric constant of HBN in situ. So I tried to actually put all these experiments on a graph, on two graphs. So the metric that I used is actually outlined in this screening paper from ICFO, where they actually measured, or they not measured, they calculated what would you expect from, like, if you calculate linear functions, and what would you expect from this on-site Coulomb interaction. So I put the stars here basically according to the angle and the gate distance, or the gate thickness. And you can see where these all these experiments line up. Basically, if you compare this to a typical experiment, let's say from MIT or from other groups, they use different dielectric constants, so they are somewhere maybe here. But if you see this, it's not super kind of obvious what these, what are these 4 papers, or what are these 4 groups did differently. It's maybe better to look into this graph, where you can now plot this, the same value of U, but now divided by some sort of measure of kinetic energy. Here, just for, because we have to rely on some theory, we just took the distance between Quantum singularities. And this kind of, maybe starts to make sense, because, you can see the Brown experiment tuned this ratio in some range, but they saw correlated insulating states. These 2 experiments, they saw some absence of some correlated states, but other correlated states are kind of still present. And the experiment that I'm going to talk to you about is basically showing no correlated insulating states. And if you think about this ratio, it's also the kind of lowest here. So you should take this graph with a grain of salt, because it's just a kind of theoretical calculation. So most likely, because of the changes in the bandwidth are not as pronounced as in this graph. So probably this curve should be shifted down, and some of this should be shifted down. But it's kind of, no matter how you define all these quantities, it seems that in this particular case that I'm going to talk, this ratio is reduced at least 2 to 4 times in comparison to the other experiments. And kind of that's the part of the correlations that I want to cover. So this talk will have like 2 parts. One is about superconductivity in this very low ratio of correlation divided by the kinetic energy. And if I have time, I'll touch upon a little bit on the Chern insulators that kind of may be related also to correlation physics. So the way how we make our devices is slightly different than other groups, and the main difference is that we use a monolayer tungsten selenide when picking up the first layer of graphene. So the end structure looks like this. You have your backgate, you have HBN on top and the bottom, and then you have on top, actually, like further away from the backgate, you have this tungsten selenide monolayer. And this is just the optical image of the 2 devices that I will talk about. For all of them are smaller than the magic angle. First one is this 0.97 degrees, and the second device has this range of contacts ranging from 0.87 to 0.79. So one kind of important point in using tungsten selenide is, it has a large lattice mismatch with graphene, so there's no Moire physics between the tungsten selenide and graphene. Effectively, it's a large band gap material, so it's kind of just, you can think of it as a dielectric, and it provides some spin orbit coupling that I'll kind of discuss more towards the end of the talk. So let's see what we see in these low angle devices. So if you start with our highest angle device, this div1, you basically see all what you're supposed to see. So you see the magic angle physics. You know, you see this is your half filling state on the hole side. This is correlated insulator on the electron side. This is 3/4. You know, and you have this superconducting pocket at on the hole side around -2 filling factor. And in all our experiments, in addition to kind of just measuring the temperature dependence, we always verify the superconductivity by basically acquiring this Fraunhofer-like pattern. This kind of is just a sanity check that we are not in some fake superconducting regime, that this is like a real superconductor. So if you can now, you know, with this device, you can kind of measure gaps, activation gaps. You can also acquire more detailed temperature dependence. You can verify that there is a linear in T scaling of RxX. And all of this just tells you, you know, the physics is kind of effectively not changed by your usual HBN encapsulated twisted bilayer graphene. So the interesting part is like what happens as you now decrease the angle. And this is a second device. You know, this angle is 0.87 degrees. And already here you can see, you know, you have still peak charge neutrality. You have insulating gaps at full filling, but now there's basically practically not much left of the correlated insulating states. There is some resistance peak here. I mean, this is still superconducting, and there is a revival of resistance peak, and this kind of relates maybe to something that Andrea mentioned yesterday. So definitely there is some correlation physics present in these samples, and if you go to even lower angles, then even this peak is maybe suppressed, but you still find the superconducting pocket around the same value. So notice that in these lower angle devices, lower than 0.9 degrees, we kind of actually switched from having a superconductivity from the hole side to the electron side. And especially for this really low angle device, there's no insulating states and superconductivity persists. And when I say there's no insulating states, I actually mean also the full filling states are not insulating. So this is just a comparison of the 0.87 degree and 0.79 degree. And these are several line cuts. So you can see for 0.87, you know, as you raise the temperature, you kind of recover this peak in the resistance. So your correlated insulating state around half filling. Then you can even recover something at 1/4 filling. But, you know, here it's a questionable whether you see and how much of the peak you can see around this. But I'll kind of comment this later on. Both of these devices, again, show this linear in T dependence. So behave in that context, they behave as the magic angle graphene. So now, you know, you can ask kind of all kinds of questions related to this physics, and, you know, whether you should think about how should you think about this physics of low angles. But I mean, there's some sanity checks that you can ask. And one of them is like, is this reproducible? So we were kind of dealing with, there are many results out there that you have like one device and basically you observe something and it's very hard for other groups or even for yourself to reproduce. So this superconductivity would be qualified as an unusual result, which kind of falls in the category that you want to verify before believe. So we had another device, basically this time slightly different, meaning that we put tungsten selenide on both sides. And we were kind of a little bit lucky that this one showed, 3 pairs of contacts all in this range between around 0.8 degrees. So you can see it's not perfectly ordered, but the disorder here is very low. And now if you compare the line traces from all these devices, kind of all checks out. Basically, the charge neutrality is here. There is no really a gap at fulfilling, and the superconducting pockets kind of line up. So that kind of, we checked out that mark. And what also is kind of important to, verify is that if you take the temperature dependence and you can see the Fraunhofer pattern, this one maybe looks even better than the previous one. But if you compare this result that I showed you in the device with 0.79 and this D4, which has all these regions here, the phase diagrams are exactly the same. So the superconductivity appears in the same places, and it's always near the half filling, and the TC is kind of also almost the same. So it's a little bit less than a Kelvin, so something about 800 millikelvin. So then the question remains, how should you think about this? And one of the questions that you could expect from all of this is, did we get rid of the correlations? So this is kind of a limit of really small correlations, because your U is much smaller than in other experiments, and also your bandwidth is much larger. So you could think of in that limit that you completely got rid of the interactions, and this is just some kind of a boring PCS superconductor, or or something that there is no there's no effect of correlation whatsoever. And okay, oops, sorry. So for this purpose, you can actually measure the hole density, and I guess this is maybe the biggest surprise of all, is that even in this low angle, even without any some significant correlation physics, you still, if you look at this region where we observe superconductivity, first this kind of color map doesn't do justice, because you still see some broad peak in RXX that kind of increases with the temperature. But what's even kind of more surprising is that you do see asymmetry breaking, or like a whole blip in this hole density, which indicates that there is some reconstruction of the Fermi surface. So at least what this tells me is that even at low angles, you can still have some sort of correlation effects. They are kind of shifted. We are significantly shifted from the mu equals 2, and maybe this actually highlights that it might be that there is some Fraunhofer's singularity physics going on, where things are kind of at low angles can move around. The other thing that I want to point out is that if you go on the whole side, you see actually very similar type of increase in resistance, but in this region there is no change of the whole conductance. So what basically that and there's no superconductivity. So this can tell you that this reconstruction is needed ingredient for establishing superconductivity. But it also tells you that if you want to get rid of all correlations just by using screening, it's going to be really hard, because you have to, if you're in the magic angle and you want to screen your interactions, you are going to unreasonably thin HBNs. So what's different in our system? And one of the things that's very different and kind of studied in context of a single monolayer graphene and bilayer graphene is spin-orbit coupling. And the way how to measure spin-orbit coupling is, by doing weak antilocalization measurements. So basically, you take some small voltage density range or backgate voltage range, and you kind of sweep around small magnetic field. And if you have spin-orbit coupling, you are expected to observe this peak close to zero magnetic field, and this is due to interference effects. So basically, we kind of found this this is in the D4, 0.8 degrees. We found the spin-orbit coupling present both in the flat bands and also in the dispersive bands. So you can kind of, this is definitely present, and it's something that when you think about the system, you cannot really completely ignore. What we believe that it also plays a role in this, that spin-orbit coupling plays a role is if you look at the Landau Fan Diagram of these devices, what we see kind of more prominent twofold symmetry, meaningly that some of the original fourfold symmetry around charge neutrality is now broken into twofold symmetry, which you would expect from spin-orbit coupling. So we see, these filling factors of 2, 4, 6, 8, 10, and even if it's the really small fields, you can see quantized conductance step in RXY. Occasionally, we see the odd steps as well. So it's a kind of combination of interactions and maybe spin-orbit coupling that plays a role in kind of defining the physics of, let's say, Landau Fan Diagram around charge neutrality. So if I think about the band structure for this system, the effects of spin orbit, can be basically summarized on this slide, where now instead of having one single, two pairs of bands, the bands, the flat bands or not so flat bands here are actually modified by the spin orbit coupling, and that, depending on now what you can, what exact type of spin orbit coupling you put in, you will have that these changes are either bigger or smaller. But what can happen, and what we are thinking is maybe happening and kind of enhancing these correlations, is that here in certain regions of the Brillouin zone, you could actually have like a flatter regions and less flat regions of the Brillouin zone, where you could have conditions for actually enhancing the interactions. So this is more of like a speculation than these graphs really suggest. But basically, whatever is the origin of superconductivity in this system, spin orbit alone without interactions cannot explain this blip in the whole resistance. So you have to have kind of some sort of interactions happening beyond that. And this actually brings me to the conclusion on this part. So what do we actually know about magic angle twisted bilayer graphene? So we know from all these STM experiments that we did and several other groups, Columbia and Princeton and Rutgers did, that even in the magic angle, the bands are not perfectly flat. So at least they are not flat everywhere. You only have parts of the band structure, so parts in the Brillouin zone that are flat, and you have a dispersive bands. And this, I was just listening to the Laura's talk this morning. You can have some.
5 minutes.
Yeah, sure.
5 minutes.
I'm actually going to be probably faster. That these patches in the Brillouin zone, they might actually play a role. One thing which you can say for sure from all these experiments that correlated insulators are kind of more sensitive to changes in this ratio than superconductivity. And at least this, the experiments that at lowest angles seem that even at the lowest angle of this 0.8 degrees, correlations do play a role. So it seems that at least we did not find superconductivity without any correlation physics. And this is mainly of the things that we kind of understand a little bit, but not fully. So what is the role of tungsten selenide? There is one practical role, is that for us, actually, it's a kind of a secret sauce that makes everything work. Ever since we switched to tungsten selenide, we definitely have better control of the angle in our devices. But, it could be that, just without tungsten selenide, you can achieve the same thing if you are cautious enough. Spin orbit coupling could make band structure flatter, or at least parts of the Brillouin zone. And we cannot, at this point, we cannot rule out that it actually enhances some part of the, facilitates superconductivity in some way that is beyond interaction, or beyond what you would expect in twisted bilayer physics. So I actually have now two routes. Either I stop here, or I kind of flash some slide about Chern insulators.
You have 3 more minutes.
Okay, perfect. So I'm just gonna kind of this part of the talk. The second part of the talk is a little bit more discontinued from this first part, but in recent a month or so, there were kind of a couple of groups that put on the archive papers about correlated Chern insulators. So these are the insulators that occur in magic angle twisted bilayer graphene, and they occur at much lower fields than when you have a twisted bilayer graphene. When you have a graphene, just monolayer graphene on boron nitride. So if you think about, this is now one of these Landau Fan diagrams that I showed you before, but I showed you only up to 4 Tesla. Now, if you go to 8 Tesla, you actually see you can be a little bit away from the magic angle, and again, you see the same physics. So I'm kind of highlighting here. This is this state that emerges basically out of nowhere at finite field, and you can have the same state for a whole side, kind of emerges on the. It requires a little bit of higher field to see, and this is just kind of a color-coded RXX. And the nice thing about this is that you can actually check the Chern number, and not only by the slope, but also the quantization. So all of these steps are actually quantized. And this is all seen in transport. And so the other thing which kind of is very important for us to check, and which we were trying to check, is and this is something that I presented kind of last year, so I kind of switched the technique from one year to another, but I want to kind of use my last minute or so to kind of go back and talk a little bit what we talked last year. So last year I was kind of presenting you with our STM work, where like 4 different groups actually in a very small period of time, published the preliminary data or some data, let's say on the twisted bilayer graphene measured with STM. And what we did very recently is now we kind of try to incorporate our technique of, having tungsten selenide beyond, below this twisted bilayer graphene, and kind of have graphite gates. So this is slight modification of our scheme, where we introduced tungsten selenide here as an immediate substrate to the twisted bilayer. And, it kind of immediately things became clearer. So this is now our kind of spectroscopy as a function of filling factor. And this is kind of complicated diagram, but you see 2 Van Hoff singularities, and then when one approaches the Fermi level, it kind of splits into branches. And for the expert in the audience, this is basically a cascade that was reported in work from Princeton. So for us, kind of immediately this became apparent when we switched to this new substrate. And then, you can now play all these tricks, as Ali's group already posted on the archive, with the Chern Insulators. So we could actually recover, so you can sit on one point and recover the Landau Fan Diagram now from STM. So basically this is a Landau Fan Diagram where you just sit on one point with your STM and you change the density and magnetic field. And one of the good things is that, these local measurements match with relatively well with all these transport measurements, but moreover kind of show you that the phenomenology of these systems, if you like put this on a different substrate, doesn't change dramatically. But it seems that, at least from all these experiences, the tungsten selenide substantially improves the quality of our devices. And with this, I actually want to stop, and I'm kind of open the session for the questions.
Thank you very much. Thanks. Okay. Let's see. There was one question from Senki.
Yeah. So what I take from all this very nice data is that the correlated insulator needs the angle to be magic, but superconductor does not. Is that right?
Yes, that's one of the takeaways.
Yeah. So actually, so do you know for all of your small angle sample, so how big is the lattice relaxation, and also how big is the angle disorder? You know that?
So the lattice relaxation is probably playing a role.
Say again, sorry.
So lattice relaxation is playing a role, for sure. So for the lattice relaxation, the best thing I can tell you at the moment is based on simulations. So in order to kind of match some of these values of the gaps, we were using Continuum model simulations, and there I actually forgot the exact numbers, but you can actually see in our paper what's the ratio of AA to AB tunneling. I think it was kind of around 0.8, no, maybe 0.5. So
0.5. Okay.
Yeah, but please verify this in a paper. So we are kind of expecting that like I should mention that, you know, this continuum model simulation you should take with a grain of salt. What we believe is that they work relatively well if you're far away from the magic angle, but at the magic angle they kind of fail spectacularly. So here we are a little bit on the lower angle, so they might actually make sense to use them, at least maybe for this case. But you know, there should be a caution when you're talking about relaxation and just this ratio. In terms of disorder, you know, this is kind of an example that I can tell you. This is one of the devices that it's best. So I would say that there's not much angle disorder here. You know, it's 0.01 degree. And I should mention that, you know, this is over quite a large area of, I don't know, 6-7 microns. Depends really where you put the start point and the end point. So yeah, kind of that's the answer.
Okay, thank you.
Yeah.
More questions?
Yeah, Stevan, I've got a question.
Yeah.
One of your one of the samples that you showed has superconductivity that completely straddles nu equals 2, and then you had the emergence of this peak at higher temperatures.
Oh yeah, this is 0.87.
Yeah, that seems really unusual because it's one thing to not. I could imagine a scenario. You know, I could imagine a scenario where the symmetry is not broken at nu equals 2 at low temperatures, and therefore you don't see the insulator, but then you see the superconductor because there's some broken symmetry at 2 plus whatever. But here it really looks like the ground state is simply superconducting at nu equals 2. And so I was wondering whether you had Hall data for this sample and what it looks like.
So I for sure don't have it in this presentation, so I can share it later. But I would say that there is still a kink, you know, in the RXY. I mean, like I would say the kink in the Hall resistance is kind of more sensitive probe than peak in the RXX. Meaningly, we sometimes see in these color maps, you know, there's not much change in RXX, but you can still see some small feature blip in the Hall resistance. So if you see a blip in the Hall resistance, it's probably there is probably some changes in RXY as well. And one of the things that, you know, now it's a kind of a little bit of a detailed question, whether, and this is also maybe present here. So I kind of shaded here this region where we see superconductivity. So now, and there's definitely Fermi surface reconstruction somewhere in the middle. But now if you want to kind of sit here on this point, you are just before the Fermi surface reconstruction, but it seems that there is some superconductivity. So
these samples are all have metal gates or graphite gates?
These are all with the metal gates. And the reasoning why we went with the metal gates is that, you know, if you have an angle disorder, this roughly translates to a charge disorder. So and it's easier to make these devices if you use metal gates. So basically, until we figure out how to basically get rid of the angle disorder, there's not much reason to do the graphene gates. In STM experiments, we do have a graphene gate. So that's the difference. In STM, it's kind of naturally to have a graphite gate. But we will probably now try to make some devices with the graphite gates as well.
Sorry, Stevan, do you, I missed it, I maybe missed at the end, I apologize. Do you have STM measurement of WSC2 supported?
Oh, yeah.
Provider?
So, well, basically, I just left two slides. One is that we observe this cascade. This is just a spectroscopy at zero field, and we see the cascade that was reported in Ali's work from Princeton. So for that, you need to have like certain sample quality to, I guess, to observe splitting of these subbands.
But what angle is this at?
1.03.
No, but I mean around the 0.8.
Yeah.
0.8. I don't have it in the presentation. We haven't analyzed the data yet. So most of the sample is at the magic angle. So we have to like look for the patches at low angles. I actually am not sure if we have such a low angle. Yeah.
I can interfere for a question for a second.
Yeah.
Going back to the same stuff. For the samples with smaller data, around 0.2, around +2, do you see any Van Hoff peak or nothing? You mentioned that you have STM data.
No, not for 0.8.
Okay.
No, sorry about this. Yeah, confusion. We have slightly lower angles where you see, still peaks, Van Hoff peaks. But I don't remember seeing 0.8 degrees.
But is there any correlation between the appearance of superconductivity and these peaks, or they are totally uncorrelated?
Again, are you asking about transport or STM?
STM.
So for STM, it's a little bit harder to say anything about superconductivity because you see all kinds of gaps and different filling. And it's hard to identify which one is superconducting, which is just a correlated insulating gap. So we are working on that. So there I cannot correlate any of these, let's say, Van Hoff singularities to superconductivity a priori. But like, for example, this would be a signature that you should have some Van Hoff singularity around this point, because otherwise I don't know how to explain the blip in the Hall resistance. Hall density.
Okay, other questions? I don't see any hand raised.
I have a question.
Please.
So Stevan, do you know at what temperature this, what you call Fermi surface reconstruction feature in Hall goes away?
Not really. We didn't do careful temperature dependence for this particular device, for the lowest angle.
I see. So what temperature was this measured at, what you're showing right now?
This is all measured at the base temperature, which is, 50 millikelvin. I mean, here's the temperature dependence of the, in a small range. But I would assume that in this range, this reconstruction persists. So it goes away at some higher temperature. But we haven't checked carefully what exactly the temperature is.
Thank you.
Yeah.
Okay. Dmitry Chichinadze.
Thank you. I have a question about the nuclear zero filling. So there were recent experiments by Andrey's group where they claimed that the charge neutrality, there are indications of the rotational symmetry break. Do you see any signatures of this kind of behavior?
So at charge neutrality, we haven't looked at this in transport so much. What we know from STM, and that's actually our Nature Physics paper from last year, is that there is this huge splitting of Van Hoff singularities when you are close to charge neutrality. And we explained that splitting, so that splitting can be viewed as a broken C3 symmetry state. Whether this occurs from like spontaneously broken C3 symmetry or from strain effects, that's a kind of a little bit murky. But our work was, in order to kind of explain this effect, you do need to break the C3 symmetry.
Okay, thank you.
Okay, more questions? Are there questions to both speakers from this session? We have 1 minute left, so let me quickly read one leftover question for Leo. Leo, are you here?
Yes.
Good. So question from Nilata Chakraborty. Does the fact that changing Coulomb screening has no effect on the slope of the linear NT behavior says anything about the strange metal versus electron phonon contribution to linear NT resistivity?
That we don't know. Unless there's a theoretical prediction of how Coulomb screening will possibly change a strange metal behavior, or how Coulomb screening will change electron phonon coupling, then our result doesn't. My understanding is that there's not. So all we can say is that Coulomb screening doesn't seem to have a measurable effect on the T-linear behavior, and that will provide constraint for possible future theoretical models.
Is there a reason why screening would affect phonon coupling?
Could change the phonon spectrum. If I don't know, I think I naively agree with you that I don't. My simple understanding, I don't expect Coulomb screening will change phonon spectrum. And I don't know how a strange metal behavior will behave when you tune Coulomb screening.
Oh, so insulator goes up. No, sorry, insulator goes down, superconductor goes up, and T-linear doesn't change. That's the basic phenomenon.
Yeah, yeah.
Okay. Thank you. You still have your hand raised. Do you want to ask more questions, or it just left over? Okay, it was probably left over. Okay, if there's no more questions, we're right on time, so let me officially end the workshop. Thanks very much to all speakers. Thanks to everyone who participated, who asked questions, or who just listened. And we hope to continue with this series. Maybe there will be second reunions and third reunion. And it's great to have, at one point, close to 300 people listening to the talks. So thanks very much to everyone, and goodbye.